Okay, Algebra 2, Set 85, Systems of Nonlinear Equations. So first of all, we're going to talk about what a linear equation is. It's a first-degree polynomial in two unknowns. So for example, it looks like y equals 2x minus 4 because the variables just have 1 degree. They're raised to only 1 power, and there are two unknowns, x and y. Another example, 3x minus 2y plus z equals 17. All the powers are only raised to the first power, therefore it is linear. Linear. Okay, so now we'll talk about equations with more than 1 degree. An equation that has more than 1 degree would look something like this: x squared plus y equals 5, or x squared plus y squared equals 7. Or you could also have it happen where some of the terms are products of variables. So you can have xy, x times y equals 4, that is nonlinear. And 4x minus xy equals 7, that's also nonlinear. Those orange and red ones are nonlinear. Okay, so we're going to talk briefly about conic sections because the most common or special nonlinear equations are conic sections, and they're called conic sections because they're taken from a cone, and it's basically the idea that you can slice a cone and you'll come up with a cross section that looks like what the nonlinear equations look like. So you can slice it any variety of ways and you'll get a conic section. So these are examples of the conic sections. The first one is a circle, so when you slice it, you can get a circle. If you look at the next one, it can look like an ellipse, which is like a squashed circle. You could get a parabola, and you could also get a hyperbola if you have two cones that are point to point. And just looking briefly at those equations, notice that they are all raised to the second power. These are also all raised to the second power. For a parabola, you have two different kinds of variables, well, like all of them, but only one of them, or necessarily like one of them would be raised to a second power. Some of them could be raised to the first power as well. And then hyperbola. And we'll actually later on get into circles, ellipses, and hyperbolas and talk about how you graph them and their special cases. So, the first thing that I want you to look at is a nonlinear system of equations is a system in which at least one of the equations is a nonlinear equation. So when we're talking about systems, when you have something that looks like that, and then you've got equations listed, it will be considered nonlinear if at least one of them is not linear. One of them could be linear. Doesn't matter. Okay? So then we have an example on this equation. Okay, so you have a circle and you have a straight line, and those are considered a system of nonlinear. And then you can see that the solution points on the circle and this straight line are where they intersect. So at these 2 points would be the solutions: 12/5, 9/5, and 0, -3, which we're actually going to solve in just a minute. So, let's see. So these are nonlinear. Here's your first example. Solve x squared plus y squared equals 9 and the line 2x minus y equals 3. So the first thing that you should notice is you've got squares and you've got variables that are not squared. So you can't just line them up and do elimination because it's not going to work. You can't subtract x from x squared. But what you can do is you can solve for y, and then you can substitute it in, which is what we're going to do. So we're going to solve that equation and turn it around so that it is y equals 2x minus 3. And then we're going to take 2x minus 3 and plug it in for y in the top equation. So you end up with x squared plus 2x minus 3 squared equals 9. Now we'll multiply that out. we'll FOIL it. So you get 2x times 2x is 4x squared, and then minus 6x minus 6x is minus 12x, and then plus 9 equals 9. So now we'll just simplify. Subtract 9 from both sides, add x squared and 4x squared. So we get 5x squared minus 12x equals 0. And now we can just come up here and we'll pull an x out of that equation. So we get x outside of 5x minus 12 equals 0. And then we can set x equal to 0, and then we'll set 5x minus 12 equal to 0. So x equals 0 is easy, it's just x equals 0. And then 5x minus 12 equals 0, add 12, divide by 5, and we get x equals 12/5. So it feels like we're done. We're not quite done yet, because so far we only have the x's. We have 0 something and 12/5 something. So now we need to find the y's. So in order to find the y's, we're going to take that original equation, 2x minus 3 equals y, and then we'll plug the x in. So for our first x equals 0. 2 times 0 minus 3 equals y. So 0 minus 3 equals y, so y is equal to negative 3. In the second one, we plug in that 12/5. 2 times 12/5 is 24/5, minus 3, which is 15/5, equals y. 24/5 minus 15/5 is 9/5. So we have our two solutions now. We know we have 0, negative 3, and 12/5, 9/5, and that's the solution. Okay, let's do another example. Now, this is an example that doesn't look like what we had before with the squared, but it does have a product of two variables. You can see it has b times td, and then plus 5 t sub d equals 25, and then sorry, can't speak correctly. b times t sub d minus 5 times t sub d equals 15. There we go. All right, so there are two ways to solve it. I'm going to show you the hard way first, and then we'll go over the easy way. Hard way, add them. We'll make the 5's and the TD's drop out. So we get 2b TD equals 40. We'll divide by 2, and then we get b TD equals 20. So we'll take that and plug it in. 20 minus 5 TD equals 15. We will subtract 15, add 5 TD, divide both sides by 5, t sub d equals 1. Now we still need to go back and figure out what b is, but that's easy. b times 1 equals 20, so b equals 20. So our solution is b equals 20, t sub d equals 1. Now that was a lot of work. And the reason why it was a lot of work is because we were using this part right here instead of this part right here. If you notice, if we eliminate the b times t sub d, we're only working with one variable, as opposed to eliminating this part and then keeping this part. Okay, so instead of eliminating well, anyway, you understand what I'm saying. I lost my train of thought, sorry. Okay, so now we're going to try it the other way. And the other way is we are going to cancel out the b times t sub d. So instead of adding, we're going to subtract. So subtract, we're going to distribute that negative sign throughout. So those b times t sub d's cancel. We get 10 t sub d equals 10. So t sub d equals 1. Now we just need to take that 1 and plug it in. b times 1 plus 5 times 1 equals 25. So we have b plus 5 equals 25 and b equals 20. Much easier this way than it is the other way. All right.